Good evening and welcome back to Vegas October 1 Sounds. In the last two videos we've been talking about ways to locate the source of a gunshot sound. And one method we used was what I called the boxing algorithm, which took successive pairs of videos for which we knew which we had synchronized, and we took the muzzle blast, the same muzzle blast in each video, and measured the time delay between the videos, and by successive pairs of those we isolated down the source of the sound via constant overlay and elimination of areas that were not possible, or that in the alternate view which were possible. Then on the most recent video I talked about Vera and method 1, which takes a single video which records both the muzzle blast and the shock wave from the supersonic projectile, and then with a lot of guessing and assumptions and everything makes an estimate of the shooting location. So tonight we're going to talk about another method, and Vera, the same Vera system as we were talking about before from Carnegie Mellon, uses a technique which is quite common in many different ways. It's not truly triangulation, but it could be considered a variant of triangulation, because true triangulation uses two angles of arrival of sound to geolocate the source. So in the scenario that we have, the question or the problem to solve is, if we have 2 points which correspond to different videos on a map somewhere, which receive a sound not simultaneously, but are receiving and recording a sound from some point, then let's call this point A on the left here, point B on the right. Then the sound travels from, up here from the source. Mark it in yellow. It travels is a bad word. It propagates to source A along that path, and it also propagates to source B along a different path. And since the speed of sound we assume is fairly constant, then the time it takes to travel from the source to each point is different, and simply the distance, which we'll call distance A here, and distance B. So the time of arrival of that muzzle blast, which I've been calling the source of sound, but let's take a muzzle blast, because that's what we're going to talk about. A muzzle blast can be modeled as a point source with a spherical propagation, and because of that spherical propagation and the speed of sound, it's going to simply be the time of arrival from the source to point A is going to be d sub A over the speed of sound. And similarly for B, it's going to be d sub B over the speed of sound. Simple stuff. C naught is what I call the speed of sound. And we could figure out the speed of sound based upon the temperature, and we can come up with a pretty good estimate. So now the question becomes, knowing that difference, we can take the difference between those two, and from that we can come up with a way of determining where the source of the sound is located. And that's the problem to be solved, and it can be solved in many different ways. And we're going to talk about one way, and that way is method number 2 in the Vera system. Okay, so we've defined the problem. Given 2 videos which are synchronized and record a single muzzle blast, and because of the synchronization we can measure the difference in times of arrival on an absolute scale, then that time of arrival coupled with the locations of the sources and knowing the speed of sound permit us to solve a problem. And that problem is, where is the locator, where is the shooter located? Now, it's not a unique solution. In fact, it's a whole family of solutions, and this is the reason. So if we have a point in common to a point of source of sound, in common to two different points, then what we know, and we have the difference of time of arrival, then what we have is for point B, we have this arc starting at point B and going over along the path of dA. It's an arc because it's a spherical propagation, which says then that the time difference between the two is the length from where that arc intercepts the path for sound A down to B. And so that's the time difference. Okay, and that time difference, which we'll call, you can either measure it by distance or time, but we'll call it delta t. Then delta t is equal to, d sub A over the speed of sound minus d sub E over the speed of sound. So we've got the makings of the start of an equation here. And the question is, how do we want to solve it? We've got 2 points in which the source, the difference in the path lengths is a fixed constant which we measured, and we measured this delta t. So for our problem, it's essentially a constant. So let's just call it k. And so now we have two variables, basically the path length to A and the path length to B, and a constant, and the speed of sound. And so the difference between those two paths equal to a constant can be framed in a series of equations. And one of the equations corresponds very nicely to what we call a hyperbolic curve. So what is a hyperbolic curve? And what I'm trying to do is give a good background to what method 2 in Vera involves and why it works and what the limitations and benefits of it are. If we, one way of looking at a hyperbolic curve is if we have a cone, if I could draw rather than just erasing, a cone, let's take a three-dimensional cone, not unlike what the supersonic shock wave produces, but in this case there's both a top and a bottom. And we then take a plane and we cut through both of the cones. Then when we look at that on a projection of what it looks like, we'll see that and rotate it 90 degrees, it kind of looks like this, where there's both the top and the bottom, and those are what we call hyperbolic curves. Hyperbolic curves and their corresponding trigonometric functions, called the hyperbolic functions, are very useful in many different applications in life. One use is for planetary motion. The Kepler's law of motion, in fact, take advantage of the properties of hyperbolas to do lots of calculations. And the basic phenomena there is that is that right enough? Anyway, if we have a planet, 2 planets actually, let's go back to yellow, I can't see the blue, 2 planets, one pink out here, and due to their gravitational attraction, one orbits around the other in something like this. And the Kepler's laws of motion basically say that if you take this path and you divide it up into segments, then where each segment is equal in the time it takes to go from point to point, so just, if we have one time, then that time is equal to this time, and I kind of drew it backwards, but I'll show you in a minute. And because of that, then the area that's swept out in each of these segments is the same. And that curve can be easily modeled with a hyperbolic function. That's one thing. That's one example. And no, I'm not even remotely close to qualified to explain planetary motion. Another use is that if you have telephone poles, two telephone poles with a wire stretched between them, this too is a hyperbolic curve. And so with these hyperbolic functions, we can predict the distance that the cable hangs down from the straight across elevation based upon the tensions placed on these wires, or inversely, if we measure the distance that the cable hangs down from that straight across elevation, then we can calculate the pressures either way. And we use hyperbolic functions to do that. In our example, we're going to use a hyperbolic curve to solve the problem of a single source of sound common to two receiving points, such that the difference in time of arrival is a constant. So, in that case, if we look at the properties of hyperbolas, and first I have to draw a hyperbola here. Let's say we have a hyperbolic curve, and we have a center point between them. That's not quite good. Okay, then we can draw a line that intersects that point and bisects these curves, and such that we can put a point here and a point here, and the distance between those points is, well, actually the distance from the middle to each point is what we call C, and the distance from the center to the point at which the curves cross the center line we call A. So we have two distances. There's one called A and one called C. And from the definition of a hyperbola, we know that twice the distance of A, i.e. the distance between these things. Oh, and I got to further define the problem before we go any further. And if we have those points which are separated by 2C, then any point along each of these curves satisfies the same problem that we're trying to do, namely the difference between path A and path B, i.e. the length of A minus the length of B equals a constant, just like and that's the problem we're trying to solve, and that constant turns out to be twice the distance of A. Okay, now in our scenario, that distance 2A is the time it takes, the time difference between the paths as we measured, delta t times the speed of sound. So therein lies the usefulness of these hyperbolic functions to solve this problem. So all we have to do then is take and find the delta t, which we do by synchronizing the videos and measuring and recording a muzzle blast, and the same muzzle blast in both of them, and then measuring the times of arrival and subtracting the two, and then that times the speed of sound will give us the distance 2A, which from this graph then we can plug into a series of equations, which I'll discuss in a later video, that basically says that every point along this curve satisfies that exact same problem. Now, if the sound were, in this case, the sound is to the right, so the solutions we want correspond to just that side of the curve, and we could erase this curve. So this is typically called F1, just the way people like to label it, and this is typically called F2. So now we have the makings of everything we need to know to solve this equation, and to plot the graph. So we have a means and a method, and the equations are trigonometric equations and algebraic equations that aren't too complex, but I really don't feel like covering them tonight is a beneficial thing. We'll cover it in part 2 or 3. So anyway, so now we know that the net result of measuring delta t, knowing the speed of sound, and knowing the locations of these things is to establish these F1 and F2, which are the locations on the map, and knowing the distance between them, which is twice c, and then knowing 2a, which is simply delta t times the speed of sound. And knowing all those things, we can plug them into the formulas for this parabolic curve and plot it. Now, not all parabolic curves are the same. Depending upon the distance between these two and the delta t, some can be really narrow, some can be really big. And okay, so knowing those concepts, let's basically figure out how we can find the shooter, because obviously a whole bunch of points are along that line, and it doesn't solve where the shooter is. So what we do is we take that table that I produced, for example, which had 15 different combinations of recording locations in the time between them for shot 1 of volley 9 verse 2. And they're all different in distance. So for example, in one case we're going to have something up here at the, well, if I could draw, we're going to have a location up here at the Luxor, and we're going to have a location down here at the Oasis Apartments. We're going to have something over here in very close to the front door of the Luxor Hotel. We're going to have a let's see, what else did I use? Oh, I used the Raymond page, which is somewhere in here, let's say, and then I used something a little further down, and now we have all these points for which we've measured delta t, and we have the distance between the combinations of them all, and we know their location. So then for each pair, we're going to take a pair. Let's say we take this pair, and in that case we could draw a hyperbolic curve just as we were talking about. So in this case, this distance between them would be 2c. That's 2c. And then from the time difference times the speed of sound, we would get where the parabola crosses on each one, and then we could draw the parabolic solution to it. Now, these parabolic solutions are fictitious, okay, because in my head I can't calculate a parabolic curve. But already knowing where they're going to point helps. But the real result would be to plot them and see. But anyway, what's going to happen is that this combination of locations and delta t and the speed of sound and the focal points is going to produce something that looks like this. Let's see which one. This one's going to arrive first, so we don't have to worry about the top one. It's going to probably produce a curve that looks like probably something like this. Okay, so anywhere along there is going to satisfy that set of points. So now if we go back, but once again that doesn't identify precisely the shooting location. It only says somewhere along this line is the most probable location for the shooter. So then what we would do is take another pair of points. Let's take the Luxor parking lot one, not parking lot, but right in front of the door, and the Raymond page, and we'll do the same thing. We will draw the line between them. Okay, which again, the distance between, this is F1 now, this is F2. Okay, and then the time between them, delta t, would establish the points at which the hyperbolas cross the axis. And then knowing those things, we could plot out, let's plot this one in a different color. Let's plot it in a little different color. That we could plot it. In this case, this one's going to come first, so we can ignore the curve, the other side of the curve on that one. And then in this case, it might be a curve that looks like this. Okay, so now we got two. And already we have a, well, if the shooting location is along this curve and it's along that curve, then only the intersections of those, namely this region in here, is a possible shooting location. And so what we would do is, much like the boxing algorithm, we would now take another pair of points, and let me erase everything in between that has to go. Alright, so then we'd take another, we already did the Luxor to what did I call it? Anyway, that point. And so on this, now let's do the that was the Excalibur up there. Let's do Luxor to the Oasis. So once again, we take and we draw that line between them. Okay, and that's then the distance between them. This would become F1, and this is F2 of the parabola. And then the delta time at which they arrive times the speed of sound would give us the vertex crossing, where the hyperbolas cross. And this is probably going to be the one that comes first. And so the parabola there would go around it, and it might look something, let's see, it might look, I don't know in this case, I really don't. So I'm just going to draw one that does something like that. So now we've got the thing crossing at a region here. So now both those solutions become possible, and with the real numbers, it's probably going to converge more closely, but even the final result may have a margin of error between it. So just like the boxing algorithm, we continue to take these pairs of delta t's and distances, and where these solutions cross becomes the most probable location of the source of the sound, or in this case, the source of the muzzle blast. So it's a really similar concept, except that the underlying mathematics deals with hyperbolic curves, their focal points, their vertices points, and those numbers 2a and 2c that govern which are the distance between the video recordings and the delta t times the speed of sound. So knowing that, you understand basically what the Vera method 2 does. And now we have to ask ourselves, okay, well, what are we measuring here? And let's erase all these things and talk about what are we measuring. Well, the first thing we have to do is, let's see, step 1, we have to align some videos. Okay, so we have to find those common visual points of reference, as I do with the marquee in front of the Mandalay Bay, and from that we produce times of arrival, TOA, they are called TOA, times of arrival of the visual event, and the times of arrival of the, we pick a point, we pick a sound, and so we get the times of arrival of the video events, and we get times of arrival of the audio events. And from that, after we do several of them, we can calculate that matrix of, if we have video 1, video 2, and video 3, just say 3 videos, then we can get the times of arrival of the muzzle blast for each of them, and every combination of them. And So for 3 of them, there's only going to be 6 combinations. Alright, and you've seen that table in my previous 6 here, T6. And then, so we have those things. Then we take, oops, so we got a table of delta T's for all combinations of videos. So the next thing we want to do then, of course, is measure the locations of each video. And so we have to have some method of locating in space these videos. And one of the easiest ways to do it is to take the longitude and latitude from Google Maps for each point, and then we can, based upon the longitude and latitude through some mathematics, convert it to either Cartesian coordinates or polar coordinates or any other kind of coordinates you want, and use those as our basis for calculating the distance between them and locating them on the thing. Because remember, we have to have 2 points, a line between them, and then we have to draw our hyperbolic curves based upon the line that goes between those points. Alright, and then the third thing we do is essentially do some calculations. Now, those calculations involve the speed of sound. They involve delta T's from above. And they involve distances, or actually, let's just call it locations. They use locations of the videos to calculate distances. Okay, now each one of these has an error associated with it. So, for example, measuring the speed of sound, we can probably measure that pretty accurately. Now, delta T, which we derived from aligning those videos, is as you'll recall, align them, is going to be off by maybe on average 1/2 frame, maybe on average a whole frame. If we really screwed up to 3 frames. So it can introduce quite a bit of error. So this one is going to be potentially pretty big. The location of the videos, Google Maps is accurate enough to give us their location down to a few feet if you could locate the video location on the map, which is a difficult process. I mean, when you look at a video, unless there's some real close identifiable marking that can be identified very precisely on the Google map, then you could be off by 100 feet in its geolocation. So this one also has a high potential for error. And then based upon the types of calculations you make, that error could be shrunk or it could be enlarged. So, but we only have to know essentially 3 things, which is the speed of sound, the delta T, and the location of that. We don't need to know the speed of the bullets because there's no shock wave involved. We don't need to know missed distances because there's no shock wave involved. So it's a little simpler than using shock wave and muzzle blast combination. It's a little bit more complex than using the boxing method. But the boxing method, once again, still has to have locations and distances. So it has this bottom part to it. But what it doesn't really, well, it kind of does rely on this. And it has to have delta T's. Because we have to know which one came first, which time of arrival was first, to determine which side of the matrix we put the little marks on to locate the source. So it's kind of equivalent to this in terms of overall error. So let's go to the Vera document, and then you can see precisely what I'm talking about. Now that you have a kind of an understanding, without going into all the mathematics, which I'll spend another whole 30 to 40 minutes just explaining the entire mathematics, along with everything that I dug out from Vera, and I have, dug out the essential algorithm just like I did for the last one. I've dug that out from Vera, and I've been programming it up. I haven't reached a point where I can do a nice, pretty curves, but I will get there within a few days. But I thought it important to explain what this is doing. So let's hop right on over to the Vera document, and you can see visually what I'm talking about. So method 2, geolocating a shooter using 2 videos is what we're talking about. And I'm going to read parts of this so that, and this is the technical documentation, which you can locate online, and I think I gave a link to it in the last video. Students from Carnegie Mellon. So method 2. Here we go. So anyway, they say that it applies when you have a pair of videos that capture a single muzzle blast common to both. And they point out that it can be used for any sound, such as an explosion, but the caveat, of course, is that it has to be a point source that's modeled with the spherical propagation path. Okay. And they say that it makes use of the definition of a hyperbola, which I just told you what it is, as shown in figure 9. Let's go down to there. There's figure 9. Oops, I might have to enlarge this a little. Okay, so now we get down to what I was talking about. The videos would be located that we synchronized would be located at F2 and F1, although I kind of swapped them. And the middle point between them would be called M, and the distance calculated by the difference in times of arrival or path length between the two, as I was talking about, would be 2A, which you can see where A is in this diagram. It's the distance from the middle point of the videos, for a line drawn between the videos, it's the middle point, to where the curve would cross the axes when you draw it. And once again here, this is an example where we have a point source common recorded by both of them, and we talk about the length from P to F2 and P to F1. In my diagram I called it something else, and it's the same exact thing, and then we divide it by the speed of sound to get the times of arrival of each, subtract the two, and we come up with delta T, which then we can multiply by the speed of sound to get 2A. Here they talk about strictly distance, that the distance in path lengths between P to F2 and P to F1 must equal twice A. Okay, and that's just the nature of a hyperbola that has a point in common to both. So, knowing that, then, what they do is they do exactly what I was telling you, is that they pick 2 points. In this case, they picked 2 that were, on the inside of the venue, and then they draw this hyperbolic curve, and noting which one, which video, in this case the blue one, where the sound arrived first, and the sound arrived second at the yellow one. But still, this would be, they have to go through all that same calculations of, drawing the line, locating the vertices, and then doing the calculations for the hyperbolic curve itself. In this case, they have 3 because they figure that the frame rate difference, i.e. 1/2 of 33 milliseconds, should be plotted also. So in this case, if you take the frame delta t time and you subtract half of frame time, then that's how you would get the other 2 hyperbolas. Okay, and then after doing that for multiple points, I better erase that crud before we go any further. Let's see, I think they show that up above. Yeah. Come on. Here we go. Here's where they plot it for multiple combinations. They use 3 points, so there would be 2 combinations, and actually it looks like they use 3 combinations. This one, and this one. And you can see how, depending upon the distance between the 2 points, the curve bends in a different way, but overall what you see is that where they intersect is going to be, let's see if I can follow this, the green line here, they intersect out there, and this one intersects there, so they have a range at which it would occur. But if I were to take, it would be that region right there. So not a real precise thing. So just like the boxing algorithm, there's going to be a margin of error that you have to kind of deal with. Alright, so that's the general concept of method 2. You understand where the errors can be introduced, and you can understand a little bit about its limitations. And I'll be going into some very real examples. I'll use the delta t's that we calculated from that table involving all 5 of those videos. And I'll go ahead and write an algorithm that'll plot them against the Vegas venue map. And I'll do the same thing here, except without that big donut that they created using method 1. So I hope that kind of explains what Vera method 2 does. And what you as a user have to do is upload 2 videos and then identify the point at which they're synchronized visually, identify the point that you want to look at that's common to both from the audio perspective, and then go ahead and let the algorithm run its course. Now there's also a compensation or an adjustment, or at least a consideration for the fact that the distance may be elevated. But this is measuring delta t's, which already has built into it the true length from wherever the shooter is, elevated or not, to the points in question, which are the recording ones. So from this method, you're going to have to make a reduction in estimation because of the elevation, if it's an elevated shooting position. And I think Vera allows you to set that, and then they adjust these curves accordingly. But that's kind of a guess, on the user's part, But, you just run through a bunch of elevations until you find the one where the curves are the closest to your data, and that's going to be the most probable shooting location. Alright, so let's review generally what we talked about in the last 3. And these are some of the equations involved. Oh, I take that back. Where do they show the equations for the hyperbola? They don't, actually. But I will. I'll show you what the equations are for calculating the x-coordinate, the y-coordinates, and based upon these things that we measured. Alright. So, let's go back to and summarize what we've talked about in the last 3 videos. We started off with a box plot, where if we have 2 points, doggone it, if we have 2 points and we do a straight line between them, and 2 points each, each point corresponds to a video recording location, and we synchronize them and we measure the delta t's, then we could determine which one of these recorded the thing first. And then we would draw a line perpendicular right across the middle, and then if this one came first, then we marked everything on that side as possible shooting source locations, everything between the middle point and this point, so that last one shouldn't be there. It would just be right up in 2. And then by taking another set of points, let's say one there and one there, and we draw the line between them. We bisect that line, which corresponds to the same thing we do kind of for the hyperbola, and then we observe from our delta t's which one came first. In this case it would be let's just say it was that one. Then we'd say everything from the point to the middle is viable, and then we would measure the intersection of the two, and we'd plot out possible shooting locations. Now in this case it doesn't correspond to Vegas whatsoever, but that intersection of those would be blah 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 blah, something like that. So that's one method without, and the only thing we have to know is delta t and locations. And that was the boxing algorithm. Then we took the Vera method 1, which we said that if you measure the muzzle blast, time of arrival, and not the muzzle blast, but the supersonic shocks, we'll put that over here, the supersonic shock time of arrival minus the muzzle equals the lag. Okay, and this is strictly in one video for 1 point for one round. Then by making some judicial choices for the speed of sound, which we can do, and for the speed of the bullet, which would be a guess, and let's see, I don't remember all the parameters at the moment. Oh well. So we need to know, let's see, thinking back, for muzzle blast shockwave you need to know, oh yeah, the most important one, which was alpha, which was the shooting angle, which is a surrogate or a replacement for shooting distance. Then we could come up with a number which we could then compare, a number for the shooting distance, and then we could compare that to the Google Maps for a hypothetical shooting location. In other words, trial and error compared to this D. So we would pick several different locations, several different elevations, and see if the numbers matched this. So it's kind of a trial and error search algorithm based upon a lot of assumptions. So you can see that this has more variables involved than the boxing algorithm, and so it's more sensitive to error. Now whether absolute error is greater, that's a whole different story. And then we covered, of course, here tonight a little bit about the hyperbolic solution. So we have 3 different methods now to estimate the shooter location, and there are multitudes of other methods. And within the next week or two, I'll have all of them plotted out on some nice graphs where we can compare them. And there's just bunches of other algorithms we can use. For example, if we take the same concept of 2 points with one source of sound, just like we would do for hyperbolic or boxing algorithm, then based upon the trigonometry of the thing, we can predict the angle, and we don't even need to know that, but we need to know the delta t's from our thing, and we can predict these angles here from some information, and then where they cross would be a proposed shooting location. And it doesn't produce a family of curves, it produces more of a precise location. But you have to have some other parameters defined pretty well to do it. So that's what would normally be considered triangulation. And you can do that with, different combinations of things to improve the resolution. Multilateration would involve, more than 2 points. It would involve three or more points, which again can be solved with a multitude of algorithms where we have a source of sound somewhere, and then we have 3 or more places which record that sound, and just like we do for the parabola, we can measure the times of arrivals at each point, and then knowing the distance between these points, we can then make form a series of equations, at least 3 equations with 3 unknowns, and we can come up with answers using the same exact techniques that was used in Vera algorithm 1, but with more equations and more unknowns, and we can come up with a pretty good estimation of the distance to the shooter. And then there's, and that's based strictly on muzzle blast. And then there's, there's quite a few others. But anyway, I don't want to get too complex. So anyway, tonight's video was about the second method in Vera, using hyperbolic curves and pairs of delta T's from pairs of videos, and using more than one pair to hone in on a probable shooting location for the source of a sound, which is a point source with spherical propagation. So shock waves are out. They're not that way, but muzzle blasts are in. You could also use the same exact technique to isolate firecrackers or a person speaking if it had a spherical propagation. Anything that follows that model. So that's it for tonight. We'll catch you in part 2 and 3 of this, in which part 2 I'll go into the mathematics and the algorithm behind the method, and in part 3 I'll wrap it all up with actual graphs from our actual delta T's, which we derived in a previous session. All right, we'll catch you in the next one. Have a good evening.